Today we're starting Chapter 9. Chapter 9 is on tests of significance. You'll see a lot of similarities with what we just got done doing with our confidence intervals. The difference is here, instead of trying to estimate a population parameter, we're answering questions about a population parameter. So we're going to start off with hypotheses. Now, the first thing that you're going to do with your test of significance is write your hypotheses. This is the key element in any test of significance. So make sure you take the time to really focus on how to write your hypotheses correctly. So we have a null hypothesis, which we use a notation H subscript O and we call it our HO. Always a statement of equivalence, maintain status quo, and it's a statement of no change. So your HO will always be an equality. So have either mu equals something or p equals something, but it's always an equality. It's a statement of equivalence. It's maintaining what already exists. So if you already know something has a mean of 12, then your null hypothesis is going to maintain that one that you already know. Then you're testing it against something new. So what you're testing against is your alternative hypothesis using the subscript H subscript, using the notation H subscript A, and we call that our HA. It's always a statement of inequality. It states what you are finding evidence for and comes from the wording of the question. Now, because it's a statement of inequality, it can be a less than, it could be a greater than, it can be a not equal to. We never do a less than or equal to, so don't think of the inclusive inequalities, because we don't want to see if it's equal to. That's what our null says. We want to do something different than that. A less than or greater than is a one-sided hypotheses, and not equal to is a two-sided, and you should see through your readings the difference between a one-sided and a two-sided test of significance. Both of them are statements about the parameter. Make sure you're using notation about the parameter. So we're always using notation such as mu or p. We're not using x bar or p hat. Both must be set before the study is conducted or data is collected. This is what you're doing in the very beginning. You figure out your hypotheses before you do anything else. Then you gather your data and you test that data based against or testing it against your hypotheses. In the end, you either reject or you fail to reject the null hypothesis based on the p-value and significance level. So our statement at the very end is always a conclusion statement, and it will always either reject or it will fail to reject. That's the language that you must use. You can never say that you accept an alternative hypothesis. We either reject or we fail to reject the null. Your conclusion statement is always regarding the null hypothesis. It is never about the alternative. So to go through an example. Hemoglobin is a protein in red blood cells that carries oxygen from the lungs to body tissues. People with less than 12 grams of hemoglobin per deciliter of blood are anemic. A public health official in Jordan suspects that Jordanian children are at risk of anemia. He measures a random sample of 50 children. So we would be running a test. If we know that people with less than 12 grams of hemoglobin are anemic, then we would say our null is that it is equal to 12, and our alternative is going to be the inequality. So if we're checking to see if they are anemic, we would be checking against that. So our HO is mu is equal to 12, and our HA is that mu is less than 12, where mu is the true mean amount of hemoglobin in Jordanian children. Notice, since I use the symbol to denote my hypotheses here, I'm going to define what that symbol stands for. Or you can write it all in words to begin with. The true mean amount of hemoglobin in Jordanian children is equal to 12 versus the true mean amount of hemoglobin in Jordanian children is less than 12. Next example. A Gallup poll report revealed that 72% of teens said they seldom or never argue with their friends. Yvonne wonders whether this result holds true in her large high school. So she surveys a random sample of 150 students at her school. Now, I know some of you have been paying attention to whether or not there's a percentage here and using that to decide whether it's a proportion. But the key thing that you should be keeping in mind is that a proportion comes from a categorical variable, and a mean comes from a quantitative variable. In this case, they either do or they don't argue with their friends, so that makes it a categorical variable, so that's what tells us it's a proportion. So we're dealing with a population proportion, or P would be our notation that we're going to use here. And we're testing it it being Yvonne's high school against what we found in the other study. So we would have the null hypothesis is that P is equal to 0.72. And then the alternative hypothesis here. Notice they didn't give a direction. It wasn't like in the previous example where we were looking specifically for when it's less than. She just wonders whether this result holds true in her large high school. She didn't say she thinks it's more, she thinks it's less. So that's why we're using the two-sided inequality of just not equal to. And we're again going to define that P is a true proportion of teens in Yvonne's school who rarely or never argue with their friends. And one last example. When ski jumpers take off, the distance they fly varies considerably depending on their speed, skill, and wind conditions. Event organizers must position the landing area to allow for differences in the distances that the athletes fly. For a particular competition, the organizers estimate that the variation in distance flown by the athletes will be sigma equal to 10 meters. An experienced jumper thinks that the organizers are underestimating the variation. Now again, notice our variable that we're dealing with here, or our parameter of interest, is our standard deviation. And then they're telling us that he thinks that they're underestimating it. Because he thinks that they're underestimating, that's giving us a direction. So we wouldn't be using the not equal to symbol. Instead, we're going to have a specific direction in our alternative hypothesis. So our null hypothesis is that sigma is equal to 10. Our alternative is that sigma is greater than 10, where sigma is a true standard deviation of the distance jumped by the ski jumpers. So again, take the time to really get your hypotheses correct, because that sets the stage for everything else. It not only is what you're talking about, but it's also how your math is going to be done.